Hello friends, today we shall derive the Fourier theory of heat conduction for 1D, and obviously this is for a rod. For this we draw first a heater and a rod connected with it. The heater acts as a heater source and the rod is situated along the x-axis. This is the heater and along the x-axis at distance x the temperature is theta, we assumed, and at x plus dx the temperature is theta plus d theta dx into dx. Okay, now at x the temperature gradient at the point x, the temperature gradient would be like x d theta dx, and at x plus dx the temperature gradient would be some different, and this would be like x plus dx equal to ddx of theta plus d theta dx into dx. Okay, now see that heat come across the dx and get out of it, and the heat that enters the section dx is the amount of heat enters the section dx is from equal to a minus k d theta dx from the theory of conduction of heat, and heat removing or outcoming from leaving from dx section dx is minus k ddx of means the gradient, temperature gradient, theta plus d theta of dx. Okay, now heat that retained in the section dx would be the subtraction of these two values, and it would be equal to q2 minus q1. Here q1 equal to the first one and q2 is the second one quantity, and we put the value of q1 and q2. After calculation it would find out that equal to Ka d2 theta dx2 into dx. Now this heat will be used in two parts. One is to increase the temperature of the material, and other to in radiation to the surrounding. And heat used in increase the temperature of the material would be equal to rho a dx c into d theta dt. Here the quantity rho equal to the density of the material, obviously of the rod. Here is the cross sectional area or surface or cross sectional area of the rod. C is the specific heat of the material, obviously of the rod, and d theta dt is the rate of increase of temperature with respect to time. Now we change the page, and the other part of the heat, total heat, would be used to in the radiation equal to e p theta e into dx. Here is the emissive power of the material, that is how much the material emit heat. P is the sectional parameter. Theta is the excess heat of the material with respect to the surrounding heat or temperature, excess temperature with respect to surrounding. And now the total heat is equal to Ka d2 theta dx2 into dx equal to heat used in radiation and plus heat used to increase the temperature of the rod. In the previous page is like that, rho a dx c d theta dt will be summed with that, and we write is at like that. Now dividing the whole equation by rho a dx c from this part, and it will be on both. After this it will be like that, Ka d2 theta by dx by rho a dx c into d2 theta dx2 equal to ep theta dx theta c by rho a dx c plus it will be cut and it will cancel out. A cancel out and dx cancel out. K by rho c remain into d2 theta by dx2 equal to ep by rho ac. Dx cancelled out, theta I plus d theta dt. We assumed that K by rho c. Now we know that theta equal to theta excess plus theta surrounding, or total theta equal to temperature equal to surrounding temperature plus excess temperature. Now derivating over it, d theta dt equal to like this. It happens because the temperature theta is equal to constant, because the surrounding temperature is always constant for this specific time, and for this happens like that. Now we put this value on the equation to theta e. Theta will be changed with theta e replaced, equal to ep by rho ac into theta e plus d theta e by dt. Okay, no problem. Now K by rho c is assumed to be h, and it would be assumed to be mu, and this is like that, h d2 theta e by dx2 equal to mu theta e plus d theta e dt. Now we have to get the solution of this equation. To have this, we change the page. In steady state condition, means when all the transfer of heat is stopped and it comes to a steady state, and then d theta dt equal to 0, and putting this d theta dt equal to 0 at equation number 1, we get that d theta equal to 0. In equation number 1 we will be get d2 theta by dx2 into h equal to mu theta e, or d2 theta dx2 equal to mu by h theta e, and we assume that mu by h equal to m square to make it confident to make the solution, and theta obviously a e to the power mx plus b e to the power minus mx.
Okay, this question tells us that we need to design a window that's 4 feet by 4 feet and separates a room that's maintained at 25 degrees Celsius from the outside that's at 40 degrees Celsius. We're told that it's not to allow more than 5 million calories of heat to enter the room each day. Right? Assume that the glass you use only has a thermal conductivity of 0.96 watts per meter Kelvin. So as we go about starting to answer this question, we're going to have to make some assumptions. First off, we're going to assume that this is steady state heat flow, which means that it's not changing with respect to time. What that's really saying is that we are going to say that we want the temperature inside the house to stay exactly at 25 degrees Celsius, and the outside is always going to be at 40 degrees Celsius. That's probably not realistic because day to night cycles mean that the outside temperature is going to be changing. But for this problem, that's the assumption that we're going to make. So the first thing we need to write down is the equation for steady state flow of heat. This is called Fick's first law. So Q is going to be equal to negative kappa, our thermal conductivity, multiplied by dt over dx, right? Now technically, we know that Fick's first law has to do with flux of something, and flux is an amount of something per area per time. But in this equation, Q, that's just an amount of something. That's not per area per time. So technically the correct way would be write Q per area per time, right? Sometimes that gets left off, but the units actually don't work out on the left-hand side to equal the units on the right-hand side if we don't account for that. So with that said, how do we go about solving this question? Well, we're told to design a window, but we're already told the dimensions in terms of area. We know how big it is in terms of area. So what can we actually change? We're not changing the temperature on either side. The only thing that we can change is the thickness or the choice of material. And in this case, we're given a choice of material. So the only thing we can change is the thickness, so dx. That's the only thing we're going to change here. So let's go ahead and start putting in values for the things that we know. First off, you'll notice that for this equation, for this type of equation to work, we have to get our units correct. For example, the total heat that we're allowed to enter the room is in calories. But if you look at our thermal conductivity, that's given in watts per meters Kelvin, right? Watts is joules per second. So we should probably go ahead and convert from calories to seconds, or from calories to joules, or from joules to calories. Let's go calories to joules. We know that 1 calorie equals 4.1868 joules. Therefore, total Q, that's going to be equal to 5 times 10 to the 6th multiplied by 4.1868 joules. That will cause the calories to cancel out, and we'll be left with just joules. I get this value to be 2.09 times 10 to the 7th joules. So 2.09 times 10 to the 7th joules. Okay, so that's the total amount of heat that's allowed to enter per day. Now, similarly, on the area side of the window, we have 4 feet by 4 feet. But on, again, the right-hand side, our thermal conductivity has units of watts per meter Kelvin, meter. So let's go ahead and make sure that we convert our feet to meter right now. So 1 foot is equal to 0.308048 meters, right? And then the other one is time, 1 day. We should put that into seconds because a watt is a joule per second, right? So we need to turn our time unit from day into second. So we know that there's going to be 24 hours in a day. Let's do our conversion. There's 1 hour and 60 minutes. There are 60 seconds in 1 minute. And so this allows us to cancel out everything except for seconds. And in 1 day, I'm going to scroll this up a little bit. In 1 day, I find that there is actually 86,400 seconds. 86,400 seconds. Okay, so now that we've done those conversions, we are ready to get started. So let's write out Q over here. Q on our left-hand side is 2.09 times 10 to the 7th joules. That's going to be divided by 4. Turning that into meters is going to be multiplying it by 0.3048 meters. That whole thing is going to be squared. That will give us meters squared. And then we have time, 86,400 seconds. So that's the left-hand side of the equation. What will the right-hand side of the equation be equal to? Let's move this up. Well, it's negative kappa, so that's going to be negative 0.96 watts per meter Kelvin. And we know that a watt is just a joule per second, so let's actually rewrite it. That's a joule per second. We need to multiply this by the difference in temperature. We know that the outside is 40 degrees. That's going to be minus 25 degrees on the inside. And this is going to be over some distance x, negative x. That's the way that we've written this equation. Since we're saying that heat is flowing down the temperature gradient, that's why we have the negative sign in front of the thermal conductivity here, and that's why you end up with a negative x here for the thickness. So when we go ahead and simplify things, the left-hand side of our equation simplifies down to 163 joules per meter squared per second. And on the right-hand side of the equation, it simplifies down to negative 14.4 watts per meter, which we already decided was a joule per second per meter. Joule per second per meter. And that is going to be then divided by negative x. So we can solve for x just by bringing it over. So let's take away the negative sign on both sides, and we are left with just x equals 14.4 joules per second per meter divided by 163 joules per meter squared per second. So joules cancel, seconds cancel, one of the meters cancels, and we're left with just our final answer of, give ourselves a little more space, x is equal to 0.0883 meters. Or if we convert that to centimeters, since it's easier to think about a window in centimeters, that is 8.83 centimeters. So that is a really thick window. In this problem, given the glass that we were asked to use, we actually had to generate a thickness which is really quite thick. So if you wanted to make your home that same efficiency, but with a thinner window, you'd have to move to a material which has a lower thermal conductivity. And that's why they use things like double-paned glass. Double-paned glass has that same silica glass or something very near to it on the outside, but it's got an air gap in the middle, which is thin, and it's a very poor conductor of heat. Sometimes they even fill that, instead of with air, they'll fill it with an inert gas like krypton or argon or a vacuum, different ways. And that would now become a double-paned window. And you can do triple-paned and make it even better. Or you could even move away from silica to something like polymers. Many polymers that are transparent have much lower thermal conductivity. But those are the things you would have to do if you wanted to have the same low flux of heat with the same dimension of your window, but making it thinner. Okay.
So we're talking about the physical mechanisms of heat transfer, and we're looking at conduction, the first method of heat transfer. And what we're going to do now is we're going to write out one of the equations that we quite often use when we're examining conduction. And it is referred to as being the conduction rate equation. And the equation that we use is Fourier's law. And writing it out, this is written in one dimension. We can have it in three dimensions, but we're writing it here in one dimension, and that's why if you look here, we have the little x. That denotes the fact that we're in the dimension or direction x. And we have this constant k, a is the area, and then dt by dx, a gradient. So what we're going to begin in looking at this equation, we're going to write out a little schematic showing the temperature with the distance in a solid. So let's assume that we have some solid and we have temperature, and then we plot distance along the horizontal. And if we could measure the temperature, let's say we measure T1 here, and then a little further into the solid we measure T2. And what we find is for one-dimensional conduction, oops, I didn't do a very good job of that, this should be a linear line, a straight line. So there we go, that's a straight line connecting x equals 0 to x equals L, T1 to T2. And then remember, the heat is going to flow from the hotter to the cooler, and consequently the heat transfer is going in this direction here. And we will take a look at the different terms in Fourier's law. We have Qx. That's referred to as being the heat transfer rate, and that could be in watts or joule per second. We already talked about that in an earlier segment. The next term that we have is K. K is the thermal conductivity of the solid that we have, or the material that we have the heat transfer going through. And the units of K are going to be watts per meter degrees C, or it could be watts per meter Kelvin. And the next term that we have is the cross-sectional area through which the heat is being transferred through. So that's the area of the surface. And that will be in units of meters squared. And then finally, we have dt by dx. That is the temperature gradient in the direction of heat transfer. And that is what is driving the heat transfer to take place. And the units there are degrees C per meter, or could be Kelvin per meter. Given that we're looking at a difference, it doesn't matter if it's degrees C or Kelvin. So that is the Fourier's law. It's a law, an equation that we're going to use over and over and over again when we are analyzing many, many different systems in heat transfer, especially when we're looking at conduction. So the different terms in Fourier's law, and then that is for one dimension. We'll get to a little bit more of a complex form of this equation when we look at the heat diffusion equation, and there we would have it in multiple dimensions. But for right now, we'll consider it only in 1D.
The next segment here on thermodynamics is another closer look at the triple phase diagram for water. And just to give you a little bit better understanding what a triple phase diagram is, it's a diagram that has on it the three phases of water. We have solid, we have liquid, and we have vapor. Notice that only at very high temperatures, water actually becomes a gas, but it's in vapor format when it's less than 374 degrees and below a certain pressure. So on the vertical axis, we have pressure in atmospheres. Notice that one atmospheric pressure is this line right here. And on the horizontal axis, we have the temperature scale in centigrade degrees. Notice the freezing point of water and the boiling point of water at 1 atmosphere. So, how is this diagram helpful? Well, for one thing, it has this line right here, which is the dividing line between solid and liquid. And notice that it's sloped to the left, or it has a negative slope if you go from left to right. Normally, for all of the substances, this line tends to be to the right. It has a positive slope. So what does that mean? Is let's say we have a solid piece of ice, frozen water, and we subject it to a lot of pressure. Notice as the pressure increases, eventually you reach a point where the solid will turn into a liquid. That's when you overcome the bulk modulus of frozen ice. Notice that the colder the temperature, the larger the pressure required in order to melt the ice, and we've mentioned that before. Also, let's say we have a vapor and you apply enough pressure to the vapor, then of course eventually the vapor will turn into a liquid by compressing it, and that's normal for all substances. The only thing that's different here is this line that is sloped to the left as you go up. Also notice that the triple point of water occurs right here when the pressure is 0.006 atmospheres and the temperature is just 1/100th of a centigrade degree above zero, above not absolute zero, but 0 degrees centigrade. At that particular temperature and that particular pressure, all three phases of water can exist at the same time. You can have solid, liquid, and vapor all at the same time. Also, what's interesting about this is about the atmospheric pressure of Mars. So Mars could have situations where water can exist in the liquid, the solid, and vapor phase all at the same time, or very nearly so. Let's see here. Notice also that at 1 atmosphere of pressure, if you have liquid water, you go above 100 degrees centigrade. Of course, what happens then is that the water will begin to boil and completely turn from liquid into vapor. Maybe you can draw a line like this. Let me try that again, right there, like so. And notice that if the temperature is less than 100 degrees centigrade, then water will not boil unless the pressure is lower. So when you go up in the mountains where the atmospheric pressure is less, then you can see that water will begin to boil at lower temperatures. So that gives you kind of a quick overview of what the triple phase diagram for water looks like and how you can utilize it. And basically tells you how you go from one phase to another depending upon how the pressure changes or how the temperature changes.
In this video, we're going to talk about phase diagrams. Phase diagrams are a type of graph that relate pressure and temperature to the state of matter for a given substance. And so this is a phase diagram. On the y-axis, we graph the pressure, and so pressure is increasing as we move up. And on the x-axis, we include temperature, and so temperature increases as we move from left to right. And there's a couple of interesting things that we can see with a phase diagram. We could tell the state of matter for a substance at a given temperature and pressure. So for example, this represents water, this phase diagram. And so on this graph, right about here would be standard atmospheric pressure, which would be 1 atmosphere or 101.3 kilopascals. And then right about here would be 0 degrees Celsius, and so that's the freezing point of water. Now, if we connect these lines, we can see that they meet right about here. And if we look at the boundary, this is the boundary between the states of solid and liquid. So this line right here represents melting and freezing. So at 1 atmosphere, standard atmospheric pressure and 0 degrees Celsius, we could say that is the melting point and the freezing point of water. Now, if we extended this line right here at 1 atmosphere out like this, we're going to get to another point here. And if we bring this line downwards towards the bottom, I think we can make a prediction as to what the temperature would be. We're on the line where a liquid is going to be turning into a gas. So we're going to cross this barrier, which means we're going to have boiling. And so this would have to be 100 degrees Celsius for water, because that's the temperature that water boils at. Now, there's some other interesting things here. So we have these boundaries where we can have solid turning to liquid, liquid turning to gas. We can even have solid going straight to gas. We call that sublimation. We also have a point right here where all the different lines converge, and we call that the triple point. At the triple point, we actually get solid, liquid, and gas all existing at the exact same point. The triple point is a really amazing phenomenon, and it happens at a very low pressure and low temperature for water. So we're way down below atmospheric and a little bit less than freezing for water. And we would literally see some liquid water that was frozen on top, so some ice, and we'd see it bubbling away as it boils as well. There's one other point that we could see here, and this is called the critical point. At this point right here, we no longer have a liquid and a gas existing at the same point. So if you can imagine boiling water, like in this kettle right here, we can see that we have both states of matter. There's liquid water, and you would probably see the steam rising, which is that vapor, as the liquid turns into a gas. Now, once we hit the critical point and we move out beyond this area, so if we're anywhere kind of in this region right here, we're going to have something called a supercritical fluid. And that supercritical substance is at the point where there's no longer a separation between liquid and gas. It just kind of becomes one thing. So it's kind of halfway between a liquid and a gas. So this is our phase diagram. That's some of the information we can gather from it. Some of the ways that we can change states include, number one, heating. Now, this is probably the most common one. If you take some water and put it into a pan like this, put it on the burner, we're going to start raising the temperature. And so if we're sitting here with frozen water at this point and we just don't do anything to the pressure, we just start raising up that temperature, we'll eventually turn that substance into a liquid. Now, we can also leave the temperature alone, so not adjust the temperature at all, and simply change the pressure. So here's an example of this. This is called a bell jar, this apparatus, where we have this plate here that have a bunch of holes in the top, and this jar, this glass jar that would fit over top, and we can create a vacuum inside that jar. So if we took a glass of water, put the bell jar on top, we'd have to attach here a vacuum. So we have this vacuum here that would start to suck out the air from this bell jar, lowering the pressure, so the pressure would decrease inside this jar. We could change this substance state without even touching the temperature. So maybe we're right here at standard pressure. It's hot enough to be a liquid, this water inside this glass, and we slowly lower the pressure. We could eventually turn that substance into a gas, and we could start boiling it without even changing the temperature. We'll take a look at one last comparison here. We have two different phase diagrams, one for H2O, water, and one for CO2, carbon dioxide. Each substance is going to have a different looking phase diagram based on its unique properties. So for water, we can have water changing from a solid to a liquid at standard pressure. So remember, this is 1 atmosphere, and we had right here 0 degrees Celsius. And so at that point, we can see it's going to melt, right? It's change from a solid to a liquid. With CO2, if we had 1 atmosphere of pressure, that's standard pressure, and we started heating up that CO2 at standard pressure, it would pass directly from a solid to a gas. And this is why, if you've ever seen CO2, another name for it is dry ice, you can see it just starts kind of giving off smoke. So you may have seen something like this before. This is dry ice that's subliming. It's turning straight from a solid into a gas, and we get all that different vapor there. So every substance has a different looking phase diagram, and you can change the state of a substance by changing the temperature or changing the pressure. And so those are phase diagrams.
All of the phase changes we've been doing so far have been under constant pressure conditions, and in particular with the problems that I've been doing with water phase changes in the last couple of videos, it was at atmospheric pressure, or at least at sea level atmospheric pressure, or at 1 atmosphere. So it was done, well, I'll explain this diagram in a second. But we all know that in the universe, pressure isn't always constant, and it definitely isn't always constant at 1 atmosphere. 1 atmosphere was defined as the pressure at sea level on Earth. Obviously, pressure will vary wildly if you go to smaller planets or larger planets, or atmospheres that have thicker atmospheres, or if we're just doing different types of applications dealing with gases and liquids and solids. So what I've drawn here is a phase diagram. Let me write that down. Phase diagram. Phase diagram. And there are many forms of phase diagrams. This is the most common form that you might see in your chemistry class or on some standardized tests. And what it captures is the different states of matter and when they transition according to temperature and pressure. And this is a phase diagram for water. So just to understand what's going on here is that on this axis I have pressure. On the x-axis I have temperature. And at any given point, this diagram will tell you whether you're dealing with a solid, so solid will be here, solid. A liquid will be here, liquid, or a gas, For example, if I told you that I was at, if I was at 0 degrees, let's say 0 degrees is right there. If I'm at 0 degrees Celsius, and 1 atmosphere, where am I? So 0 degrees, 1 atmosphere, I'm right at that point right there. So I'm at a boundary point between solids and liquids at 1 atmosphere of pressure, right? This is when we're at 1 atmosphere of pressure. So this coincides with our traditional notion of when ice freezes or when it melts at 0 degrees. If we made the pressure higher, what happens? Well, then ice starts melting at a lower temperature, right? So this is pressure going up. So pressure going up, let's say, I don't know what this is. This is maybe 10 atmospheres, 10 times Earth's atmospheric pressure at sea level. Then all of a sudden, the temperature at which solid turns into liquid, right? This transition is solid to liquid. The temperature at which that happens will go down. Likewise, if we lower the pressure, if we go to Denver, it's a mile high, pressure is lower because we have less of the atmosphere above us, then all of a sudden the the freezing point increases. So the freezing point will be something above 1 degree. And this isn't drawn completely to scale, but the idea is your ice would actually freeze a little bit faster and would freeze at a higher temperature in Denver than it would at the bottom of the Dead Sea or in Death Valley at some very low below sea level point on the planet. Now, this transition is a transition between anything and gas. And we're very familiar. This is 1 atmosphere. And remember, this is water we're dealing with. This is the diagram for water. So at 1 atmosphere, this is kind of the stuff that we're used to seeing. Let me draw a line here. So at 1 atmosphere, 0 degrees is where solid or ice turns into liquid water. And then we go up here. So we keep going to higher temperature. And then here, this would be, since we're at 1 atmosphere, this is 100 degrees Celsius right there. And that's the point at 1 atmosphere pressure where liquid turns into gas, or water vaporizes, or the liquid boils. All of those are acceptable ways to think about that. But what happens when we go to low pressure? Once again, let's take our little trip to Denver, right? So that's Denver right there. Denver. And it's not that drastic. I'm just doing that for education purposes. Or even better, let's say Mount Everest. Mount Everest, very low pressure there. Then Our freezing point, we already said that goes up when you lower the pressure, and your boiling point goes down. So it's much easier to boil something on the top of Mount Everest than it is to boil it at the bottom or at the lowest point in Death Valley or the Dead Sea. And the reason, the intuition behind that is if I have a liquid, a bunch of molecules in liquid form, and they're touching each other, but they have enough kinetic energy to move past each other. So they're moving, they're flowing past each other. They're kind of rubbing up against each other. One of the reasons why they don't just evaporate, why this guy doesn't just jump up there, is that there's air above him. There's air pressure. And air pressure, we've learned about this when we did PV-nRT. That's a bunch of gas molecules, and the pressure they're creating is essentially caused by their temperature and their kinetic energy, and they sit there and they bounce, and they essentially keep these heavier molecules from going up. They keep them from essentially separating from each other and turning into a gas. So the more pressure you have, the harder it is for these guys to escape. On the other hand, if you have if we're in a vacuum, if we're doing this on the surface of the moon, and there's none of these guys there, then just a little slight bump, even though this guy is still a little bit attracted to over here, they're still attracted to each other, but just a little bit of bump, since there's no pressure up here if we're on the surface of the moon, might allow this guy to escape and go straight to a gas. So when you lower the pressure, it's just that much easier to go from liquid to gas, or even from solid to gas. And you might say, Sal, that's a bizarre concept, solid to gas. And it turns out if you get to low enough pressures here, I mean, let's say there's probably not stuff here. This is probably close to a vacuum right here. You could go from ice. So if you took ice and you were on the moon and you were at the right temperature, this is, maybe some negative degrees Celsius temperature. I don't know what the exact temperature is. Your ice on the moon would go directly from ice to a gas, because there's this huge vacuum here. So these molecules will say, hey, there's all this space to fill, and if they just get bumped a little bit, they're just going to escape and turn into a gas. And you might say, oh, Sal, that's a strange phenomenon. It only exists on the moon. And because to rebut that comment, I've drawn the phase diagram for carbon dioxide. Carbon dioxide. It's all around you. You're exhaling it as we speak. Your plants in the room are hopefully inhaling it. But carbon dioxide at 1 atmosphere has a very different behavior than water. This is carbon dioxide at 1 atmosphere. And just so you know, this scale is definitely not drawn to scale. The difference between 1 atmosphere and 5 atmospheres is not the same between 5 atmospheres and 73. Likewise, this is not drawn to scale here. This is a much larger distance than this. So if I had to really draw it to scale, I have to stretch this chart out or do a logarithmic chart or something. But anyway, I was talking about carbon dioxide. So this is carbon dioxide solid, and this is gas, and this is liquid carbon dioxide. So at 1 atmosphere, if in like, let's say you live at sea level, you're in New Orleans, I guess it's a little bit below sea level, that's where I grew up. If you were able to get your fridge down to minus 80 degrees Celsius, the carbon dioxide would actually freeze. And you're actually not too unfamiliar with that, or at least you haven't been if you've gone to some, I don't know if they still use it for smoke machines or for visual effects on stage, but this is dry ice. Dry ice. It's frozen carbon dioxide. And then as soon as you get above, if you're at kind of a sea level atmospheric pressure, as soon as you get above this minus 78.5 degrees Celsius, it sublimates to gas. So that process where you go straight from a solid to a gas is sublimation. Sublimation. And that's why dry ice, when you see it, you don't see liquid dry ice. You don't see it at standard pressures. I've never seen liquid carbon dioxide. In order to get liquid carbon dioxide, you have to get above 5 atmospheres. So you have to get above 5 times the sea level pressure on Earth. And you're really not going to see that in natural conditions on Earth. You might see that on Jupiter or Saturn, where you have tremendous pressures because of the gravity and all of the atmosphere above you. So this is the kind of thing, liquid carbon dioxide, you might see, I don't know if Jupiter actually has carbon, but you'll probably see it on other huge, massive planets that are gas giants. But on Earth, this process is just called sublimation. It's just a neat word, or it's sublimating. It's going straight from solid to gas, and it's something you've seen with dry ice. Now, there's a couple of other interesting points here, and you're probably already noticing them. And this right here is called the triple point, because right here, at this well, in the case of carbon dioxide, at 5 atmospheres and minus 56 degrees Celsius, the carbon dioxide is in a state of equilibrium between the ice, the liquid, and the gas. It's a little bit of all of the three, and if you just nudge it in one direction or another by nudging the pressure, the temperature, it'll go in that direction. Similarly, water's triple point is right here. It's at a much lower pressure than we're used to dealing with. This is 611 or 0.611 kilopascals, or just 611 pascals, which is, not 5 thousandths of an atmosphere. So if you go down to 5 thousandths of an atmosphere and you go a little bit above 0 degrees Celsius, you're at the triple point of water, where water can take on any of these states, where it's if you just nudge it one direction or another. Now, the other interesting point on these charts is up here. This is the critical point. Sounds very important. Critical point. And that's the point at which, if you increase the temperature beyond that or the pressure beyond that, you're dealing with a supercritical fluid. Supercritical fluid. Sounds very exciting. So above here, you have a supercritical fluid. So very high temperature, very high pressure. So it's so high temperature that it wants to be a gas, but you're putting so much pressure on it that it wants to be a fluid. So it's a little bit of both. And actually, in the case of water, supercritical water is actually used as a solvent, because you can imagine it's kind of like liquid water in that things can dissolve in it, but it's so high temperature and it can diffuse into solids that it's really good at just, getting whatever you want out of whatever you're trying to clean or somehow get into or I guess get salt, put into the water. So this is supercritical fluid, and it's a fun thing to think about. But anyway, I just wanted to expose you to these phase diagrams. Actually, let me just everything I've done so far was at a constant pressure and I changed the temperature, but you can also read them the other way. If I'm at 100 degrees and I go from, or let's say I'm at 110 degrees, we're at sea level is comfortably in the gaseous phase so this is 110 degrees for water, it's water vapor. But if I were to increase the pressure, and I keep increasing the pressure, and maybe I dig a hole or something, or go into the ocean, then it's going to condense into water, or it's going to condense into a liquid. If I did that experiment here, well, that's probably, let's say I did the experiment here. When I increase the pressure, I'm going to reverse sublimate, and I think I wrote down a word for what that is. Let me see if I wrote it down someplace. Oh no, I didn't write it down. But essentially, it's something like condense. But my brain, the word is escaping me at the second. It's something on the word of condensing or falling together. Anyway, I forget the word. But it will go straight from a gas to a solid. So these are pretty neat diagrams. They actually tell a lot about different substances and tell you what happens when the pressure or the temperature changes.